the cloud. And I'm just going to turn it into the writing format. And let's now return to where we last left off. So we'll be resuming on page 15 of the notes. So we're on page 15 of the notes. And what we're going to practice today, what we're going to do a lot of practice of, is drawing chair conformations of cyclohexane using dash wedge notation. Now, it's really important that we do not conflate dash wedge with axial or equatorial. So when you see this wedge, it means our bond is pointing up out of the plane of the page. So for example, if our page was a piece of paper, the wedge bond is going out of the plane of the page. So it's pointing up out of the page towards us. So to give you an example, of what a wedge would look like from a practical perspective, if we view our cyclohexane ring, this is methyl cyclohexane, my question to all of you, from your view, is this methyl group pointing above the plane of the page or below? Is it pointing up or down? And you're welcome to type in chat during this time. Up, yep, exactly right. So if we're viewing this from the perspective of the plane of the page, the methyl group is pointing out towards us. It has a wedge. It's going towards you from your view. Does everyone notice how from this view, the methyl group is closer to you? The methyl group is pointing out towards you. So that's what the wedge notation is saying. This group is pointing out of the page. Okay, now, if we're drawing the wedge, so this wedge is, so it's pointing up out of the page, we can choose to place it in the axial up position, or, okay, so this is our first option. So it's axial pointing up. So for example, it would look something like this, axial pointing up. Now, we can just as easily perform a ring flip. So I'm going to move my blue carbon up and I'm going to push my yellow carbon down. And now my question to all of you is, even though this methyl is still up, is it axial or equatorial now? Is it axial or equatorial? Yep, it's equatorial. Now, let's focus in and let's zoom in, and I'd like you to compare this hydrogen and our methyl group. So my question to you is, from this view, which substituent is closer to you? This methyl group or this hydrogen back here? Which one's closer to you? Which one's pointing out of the page? The methyl group, exactly right. So this methyl group is equatorial, but it's still pointing up. Does that make sense to everyone? Anyone have any questions so far? And I really encourage you to make a model of the cyclohexane ring and play with it at home. Now, unlike the wedge bond, for the dashed bond, our bond is pointing down below the plane of the page. So for example, if here's our page, yes, the switch from axial to equatorial is the result of a ring flip. Yes. But the key thing that's really important to take away is no matter how we flip, how we undergo a ring flip, let me start from scratch here. So here's our original structure before the ring flip. The methyl is up. After a ring flip, the methyl is still up relative to our hydrogen. So the ring flip only changes the axial versus equatorial position. It does not change the stereochemistry, whether it's dash or wedge. And that's a really critical thing to keep in mind. So let's look for comparison what the dashed notation indicates. So the dashed bond indicates the bond is pointing down below the plane of the page. So to give you an example of what a dashed system would look like, let's put an OH group on our methyl ring. Let's put an OH group on our methyl ring. So from this side-on perspective, is the OH pointing up on top, or is it on the bottom of our ring? Is our OH pointing up or down? Yep. So then, what notation would we note this OH as? With a wedge or with a dash? If it's pointing down. Yep, exactly right. If it's pointing down below the plane of the page, it gets a dash notation. Now, this is one way of representing our dash notation. Let's now do a ring flip. So what we're going to do is we're going to bring the yellow carbon up, and we're going to push our blue carbon down. Okay, so we've now done a ring flip. And my question to all of you is, what position is our OH in? Is it axial or equatorial? Let's take a moment looking at this OH. Is it axial or equatorial after the ring flip? Yep, equatorial. Now, compared to this hydrogen, let's view this from the perspective where we're staring directly into the page. Which of these two groups is closer to you, the hydrogen or the OH? Which of these two groups gets the dash? Okay, the hydrogen's closer. So then, what notation do we give this OH if the OH is going into the page? What do we call it when it's into the page? Yep, dash, exactly right. So then, we have two potential positions for our dashed substituent. It could be equatorial, pointing down. As you notice, if we look at our hydrogen really closely, our hydrogen is axial, pointing up. So we can think of it as if our hydrogen has the wedge. And after a ring flip, just as a reminder, carbon number 1 is brought down and carbon number 4 is brought up. So at carbon number 1, now our OH, which was originally in the equatorial down, is now in the axial down position. So the ring flip only changes whether you're equatorial or axial. It does not actually change your stereochemistry, whether your substituent is up out of the page or down into the page. Does that make sense to everyone? Anyone have any questions on this? Okay, so what I want everyone to do is to take a moment and try and draw on their own piece of paper, etc., a reasonable chair conformation. The reason why you do ring flips is you're showing the two conformations for for each of your molecules. So this molecule can exist in either of these conformations, and what we're going to do later on in this chapter is compare the energy of these conformations to assess which one of these conformations is most predominant. So the reason why we do ring flips is that at room temperature, your molecule is constantly undergoing ring flips. And we want to be able to look at both the potential conformations, both chair conformations, in order to determine which one is predominant and understand how different conformations can react in slightly different ways. Does that make sense? Okay, perfect. So let's take a few minutes. Let's take about 2 minutes, and using the guides that I provided to you, I'd like you to draw the chair conformations for the following molecule. And really focus on noting what this wedge symbolizes. And when you're ready to share, there are a few options. What you can do is you can request a share, you can annotate, and you can annotate in this blank space provided your answer and just write your name next to it. All of these are viable options. So take a moment and try to draw the chair conformations, and you're welcome to even unmute your webcam and hold your paper up to the webcam, and I'll be more than happy to check your work. I know for organic, it's a little hard to use the chat to convey structures, but let's take a few moments to work on this. And if someone wants to volunteer, you can use the annotate function and just write out a sample chair conformation, and I can look it over. Anyone want to volunteer? Anyone want to volunteer? And don't be shy. Anything is a good source of discussion. Okay, so all you have to do is hit the annotate function, and you can try drawing out one of the chair conformations. So one thing that is always nice is you can choose to put your substituent at carbon number 1. So you don't have to worry too much about, would someone else like to propose another chair conformation? I just want us to have a few to discuss before. I'm not to say, not remote control, just the annotate function. Yep, you're more than welcome to. The annotate function is open to all students. It's a little pen button called annotate. And don't be shy, while one person is drawing, another person can also draw. No, you can also do it with your computer, as your mouse also serves as a drawing tool. So as long as you have a mouse and keyboard, you're more than welcome to chime in. Let's take about 1 more minute to try drawing the conformation, and don't be shy, multiple people can annotate the same document. It's no problems at all. So to help everyone along and to provide a little bit of clarity, so in the view options button, there's an annotate button. So what I'm going to do for now is I'm going to, you can draw. You can draw. I'll keep it open. Okay. Okay. And then could you draw the hydrogen as well? Oh, just the hydrogen on the carbon attached to the sulfur. Just this one right here. Okay, so let's talk about this example. This one, what was drawn here is actually the wedge notate, the dashed notation. So let's talk a little bit about that really quickly. One moment. So let's talk through this example and then I'll show how to access the annotate function. So we have a wedge notation here. So we're going to draw our cyclohexane ring and I'm going to label carbon 1. Okay. Now, the wedge tells us that our substituent is pointing up. So we're going to draw our SH in the axial up position. And our hydrogen is pointing down by default. Because if one substituent is pointing up, the other substituent will be pointing down. If we want to undergo a ring flip, so we label carbon 1 and carbon 4. So carbon 4 moves up, carbon 1 moves down, and we end up with the following conformation, the following chair conformation after ring flip. So now our hydrogen is still pointing down and our thiol group is equatorial, but still pointing up. So one trick that I want you all to employ is to put your substituents at carbon 1. It just makes things a lot easier by default. You can rotate your molecule around and it makes it a little bit less cumbersome to draw chair conformations. The other thing that I want you all to do is to draw your hydrogens. If you draw your hydrogens, it gives you a really fast way to check your work. I know that my thiol is up because this hydrogen is equatorial pointing down. Likewise, I know my thiol is up because my hydrogen after the chair flip is axial pointing down. Does that make sense, everyone? How to check your work and why drawing your hydrogens is super important? So in the student solution, it was almost perfect. The only thing to keep in mind is you want to make sure you draw your hydrogen in the proper position. And you want to make sure that if your substituent is pointing up, your hydrogen is pointing down. Let's do another example. And to help us along with this process, what we're going to focus on next is we're going to do a discussion of cyclohexanes with 2 or more substituents. So we're going to increase the complexity slightly, but you're going to begin to see some key relationships for cyclohexane stereochemistry. So the cis cyclohexane, the substituents are on the same face of the ring, both up or both down. Now, let's take a look at analyzing the following structure, and to help everyone along in this process, we're going to use a model kit. So our bromine and chlorine both have a wedge. So are they pointing up out of the page, or are they pointing down into the page? What does this wedge tell us? Are both of our substituents pointing up or down? Yep, up. So both of these substituents are quote unquote up out of the page. So here is a model. So I want you to note that the red is our bromine and the purple is our chlorine, okay? So as you can see, relative to the plane of the page, are they both pointing up? Does everyone see how they're both pointing up? Okay, now let's do some analysis. So looking at our bromine, is it in the axial or equatorial position? Is this bromine axial or equatorial? This one right here. Axial. So here we go. We have our bromine in the axial up position. Now, critically, as a check for our work, looking at this hydrogen, is the hydrogen axial or equatorial? Is this hydrogen right here? Equatorial, exactly. Now let's look behind. So looking at our chlorine right here in purple. Is this chlorine axial or equatorial? The chlorine that I'm holding, is it axial or equatorial? Yep, equatorial. So it's right here. It's equatorial up. Okay, now we're going to do a ring flip. I'm going to bring my blue carbon up and my yellow carbon, I'm going to push down. Okay, so we've completed the ring flip. Now are my bromine in red and my chlorine in purple, are they both still pointing up? Or are my chlorine and bromine still up? Are they pointing above the plane of the page? I see some students saying yes, that's exactly right. But, and this is really critical, looking at our chlorine in the back, is our chlorine now axial or equatorial? Axial, exactly right. So after a ring flip, our chlorine is axial pointing up. Yes, exactly right, exactly right. So to help you visualize this a little bit easier, if you're viewing this chair conformation, chair number 1, it would look a little bit like this. So we have our chlorine in the axial position. What about our bromine? Is our bromine in the axial or equatorial position? So looking at this bromine, is it axial or equatorial? Yep, equatorial. Yep. So our bromine is equatorial, but it's still pointing up. Now, this is really why I encourage you to build a model the first few times you're going through this, because it really makes it easy to see whether a substituent is pointing up or down and whether it's axial or equatorial. Now, let's take a look at the trans stereoisomer. So cis and trans, these two species are two different compounds. These are different compounds. So let's look at the trans. Now give me one moment to get that all set up. Okay, so here we go. Here's our trans stereoisomer. Now my question to all of you is, one moment, here we go. So what substituent is pointing up currently? What substituent is pointing up currently? Our bromine in red or our chlorine in purple? Yep, bromine. Yep, so it's axial, quote unquote, up. Now, how would we describe our chlorine? Is it axial or equatorial? Looking at our chlorine, is it axial or equatorial? Axial, yep. And my question to all of you, it's axial. Is it pointing up or down? Yep, so it's axial, pointing down. So does everyone notice how our bromine and chlorine are on opposite sides of the ring? They're trans to each other. Does everyone notice how the bromine and chlorine are on opposite sides of the ring? Now we're going to undergo a ring flip. So I'm going to bring up my blue carbon and lower my yellow carbon. And at the end of our process, let's try to describe the orientation of our substituents. So looking first at our bromine, is it pointing up or down? Is our bromine pointing up or down? Up, yep. And is it in the axial or equatorial position? Yep. So it's up and it's equatorial. Okay, let's look at our chlorine now. Is our chlorine axial or equatorial? Yep, it's equatorial. But, and this is really critical, is this chlorine pointing up or down? Yep, down. Okay, so this is another trans form, and the reason why our substituents are trans is because one substituent, our bromine, is up while our other substituent is down. They have a different stereochemistry, a different relative arrangement of atoms. Okay, So what I want you to really focus on and what you really do need to pay attention to is that when you're drawing a chair conformation from dash wedge notation, you need to make sure you are respecting the 3D orientation of each substituent. Notice my bromine had a wedge, so the bromine must always be up, up, up. The chlorine had a dash, so the chlorine must always be down. If for what? All of your substituents will flip, yes. So all of your substituents flip from axial to equatorial. We just can't see it for the hydrogens because the hydrogens are identical. But yes, that's a very good point. All of your substituents flip. So there's a table for axial and equatorial relationships for highly substituted cyclohexanes. This is a reference that you can use as like training wheels when you're getting started, but I'm going to show you a very quick ground up method for drawing any cyclohexane ring. So I want you to follow along with me for each step. And if you have any questions, this is the method I personally use. So first thing you're going to do is you're going to identify a substituent with a wedge stereochemistry. So it's pointing up. And I'm going to label that carbon with an axial label. The reason for that, and the reason why I'm doing this, is because carbon number 1 in the right facing chair conformation, your substituent X is axial up. So for example, if you had a substituent X with a wedge at carbon 1, it would always be in the axial position pointing up. So we're going to start and we're going to put this axial label here. Okay? So if you're drawing your right-hand chair conformation, your bromine or whatever substituent at carbon number 1 would be axial pointing up. Okay? Now, if you wanted to draw the ring flip form, and I honestly would wait until you're done with all of your substituents before you do a ring flip, but you can. You take carbon 1 and you bring it down. You take carbon number 4 and bring it up, and you flip all your substituents from axial to equatorial. So your bromine is now at carbon 1 and it's equatorial pointing up. Is everyone following so far? So this is really important. You want your carbon 1 to be a substituent with a wedge, and you're going to draw it axial pointing up. That way you aren't accidentally drawing an enantiomer or drawing a stereoisomer. Okay. So now what you're going to do is you're going to count clockwise around the ring. So you're going to label the adjacent carbon with an equatorial label. So you're going to put an E. So we labeled axial equatorial. Okay? Now, if that carbon has a wedge, the substituent will be equatorial. Okay? So looking at this chlorine, it is equatorial, but is this chlorine still pointing up? Is this chlorine still pointing up? Yep. So it's equatorial up. That's why we have this equatorial label for the wedge. Now, if we undergo a ring flip, the chlorine will go from equatorial up to axial up. We won't worry too much about the ring flip for right now. Okay, let's keep going. Now, you're going to count around the ring and you're going to label the next adjacent carbon around the ring with an axial label. And if that carbon has a wedge, the substituent will be axial. So you're going to repeat axial, equatorial, axial, equatorial, axial, equatorial. So this labeling applies only if you see wedges, okay? So counting around the ring, if we look at the methyl group, where would we expect our methyl group to be? Would we expect our methyl to be axial or equatorial? Yep, I see equatorial, right? We see the E next to it, so it's equatorial. So then, everyone notice here that in our right-hand chair conformation, our methyl group is equatorial, and it's pointing up. Okay, now, this is really important. This is really important. Do not, and I repeat, do not, when you draw these conformations, you need to make sure you're always starting off with an axial up. If you start off with an equatorial up, you're drawing actually an entirely different species known as an enantiomer. We'll talk more about that later, but just always make sure you're starting with an axial up substituent at carbon number 1, if you can help it. Is everyone clear on the logic so far if we just have wedges? Any questions so far? Let's check our time. Still have plenty of time. Okay, so let's keep going now. And what happens if we have some dashes? Okay, so just like before, identify a substituent with a wedge stereochemistry. So we have a wedge, so this is going to be axial up. And I'm going to prefer to place that at carbon 1 if I can help it. So carbon number 1, this bromine is axial up. That is nothing new. Now here's where the cool part comes in. So counting clockwise around the ring, we're going to label the adjacent carbon with an equatorial label. So we have axial and equatorial. However, and this is the change, if the carbon has a dash, if a carbon has the dash, the substituent will be axial. So anytime you see a dash, you change your label from equatorial to axial and vice versa, okay? So this chlorine, because it has a dash, so this chlorine, because it has a dash, will be pointing down. Now, because of that, instead of placing our chlorine in the equatorial position, instead, we will place our chlorine in the axial down position. So then, let's keep going from here. Let's now do a quick chair flip. So our bromine is axial pointing up. So after our chair flip, where we bring carbon number 1 down and carbon number 4 up. Our bromine at carbon number 1 will now be in the equatorial up position, and our chlorine will be in the equatorial down position. So does everyone notice how our counting method changes when we have a dash? Does that make sense to everyone? So if you have a dash, you change your label. So we would expect if there was a wedge, it would be equatorial. We have a dash, we change it to axial. Okay, let's keep going now. So we're going to keep going. If the carbon has a dash, so we keep labeling, so we put the next adjacent carbon around the ring with an axial label. If the carbon has a wedge, it would be axial. If the carbon has a dash, the substituent's equatorial. So counting around the ring, axial, equatorial, axial, equatorial. The only substituent that we have to flip is our chlorine. We change it from equatorial to axial. Okay, so we're going to make that change here. Change our chlorine from equatorial to axial. So the chlorine is axial down. And when we do a ring flip, our chlorine is now equatorial down. Does that make sense how this counting method changes when you have a dash? Any questions so far? Yes, all the other substituents keep the same pattern. So if we're counting around the ring, it would be axial, equatorial, etc. Exactly right. And you can even count in two separate colors. For example, the black would be for the wedge notation, the red would be for the dash notation, if you're so inclined. So let's try to apply this and let's summarize what's going on here. So if you're thinking about mapping, all the blues correspond to dashes and all the reds correspond to wedges. And if you're curious about the coding, so all the reds, you'd count axial, equatorial, axial, equatorial, axial, equatorial, alternating. And for the dashes, it's the exact opposite of the wedges. So you'd count equatorial, axial, equatorial, axial, equatorial, axial. This is a nice reference to keep in just as a little cutout in the back of your note set, just in case you're ever staring at a cyclohexane ring and you're not sure whether to put something in the equatorial or axial position. So let's take a look and let's make sure this mapping method does work, okay? So starting off, our hydrogen is axial and it's up. That makes sense so far. The next hydrogen is equatorial, up, and so forth. Let's check our dashed. So at carbon one, would someone like to tell me, is this equatorial hydrogen pointing up or down at carbon 1? Yep, exactly right. So it's equatorial down. Wonderful, wonderful. And finally at carbon 2, let's put a complete description. So let's type a description describing whether the hydrogen at carbon 2 in blue, is it axial or equatorial, and is it up or down? Let's take a moment and let's assess carbon 2. The hydrogen in blue, yep, axial down, exactly right. And that exactly matches our prediction for our dashed hydrogen. Perfect. Now, the only thing that you have to be careful of during a ring flip. So during a ring flip, carbon 1 goes down, carbon 4 goes up. So carbon 1 is now right here, and all of our axial and equatorial substituents are exchanged. So looking at this hydrogen here at carbon 1, is it axial or equatorial? The hydrogen in red at carbon 1. Is it axial or equatorial after the ring flip? So this one right here after the ring flip, this would be equatorial pointing up. Now, continuing on with that logic, let's look at the hydrogen in blue after a ring flip. So the hydrogen I've circled right here, is it axial or equatorial? Is this hydrogen in blue on carbon 1? the hydrogen in blue on carbon 1 right here. So it would be axial, and really critically here, is it pointing up or down? This dashed hydrogen, is it pointing up or down? Down, exactly right. Okay. Any questions on this map that summarizes our dash wedge notation? Okay. So to help you along with this, give me one moment. Let me make a guide for you to see. I'm just putting together the model kit right now. Give me one moment. It'll really help you to see it. So don't worry, I'm almost there. Okay. Okay, so here's an example model. So I'd like you to tell me, so here's our axial hydrogen in red. This is our wedge hydrogen. This is our dashed hydrogen in blue. Here's our second wedge hydrogen in red. Here's our second dashed hydrogen in blue. So as we can see, the red wedge hydrogens are up, the dashed blue hydrogens are down. So this is the structure that we have on the left. Now when we undergo a ring flip, now if we look and see, so on carbon 1, I'd like you to tell me, looking at this hydrogen after a ring flip on carbon 1, is this hydrogen now axial or equatorial? Is this one right here? Equatorial, exactly. So that's why after a ring flip, we have this hydrogen right here that is equatorial pointing up. And by the same token, by the exact same token, our blue hydrogen, which is dashed, is it now axial or equatorial? Our blue hydrogen, axial, yep. But is it still pointing down? Is it still below the plane of the page? Yep, exactly right. Does that make more sense now? Did that address your question? Perfect. Okay, so let's take a moment, and what I'd like us to do now is I'm going to show you a representative example, and then you'll tackle a few examples on your own. So let's show how we would process an example from start to finish. So here we go. First things first, this ethyl group has a wedge, so it's up, and I'm going to place it in the axial position at carbon 1. So I'm going to count axial, equatorial, axial, equatorial, axial, equatorial, and then I'm going to change. Since I have a dash, I'm going to count equatorial, axial, equatorial, One moment. Let me reopen OneNote. Give me 1 second here. Let me reopen OneNote. Allow me 1 moment to do that. Apologies for that slight technical difficulty. Okay, let me reopen OneNote. Sometimes it gets a little flustered when multiple things are being added to the screen. Okay, so let's just refresh. I'm going to count for wedges: axial, equatorial, axial, equatorial, axial, equatorial. For dashed, I'm going to use the opposite counting convention: equatorial, axial, equatorial, axial, equatorial, axial. Okay. Now from here, what I'm going to do is I'm going to place my wedge substituent axial up in my right facing chair conformation. It's really important that you keep this consistent. Otherwise, you'll potentially be drawing an enantiomer. So this ethyl group is axial pointing up. Now, looking at our methyl group, which is at carbon 3, is our methyl group, according to our counting method, going to be axial or equatorial? Axial or equatorial? Let's try to answer that question. Yep, equatorial. Yep. So it will be equatorial pointing down. And the way that I like to check my work with that is I like to draw my hydrogen, and the hydrogen in this case would be axial pointing up. So I like to think of it as if my hydrogen has the wedge. Both methods are valid, but I always like to draw my hydrogens out because it really helps show if I made a mistake. Now we're going to subject this conformation, this compound, to a ring flip. So remember, carbon number 1 gets brought down, carbon number 4 gets brought up, and all of our axial and equatorial positions are now flipped. So our ethyl group is now at carbon 1 pointing up, so it's equatorial. Oops. Equatorial pointing up. And our methyl at carbon 3 is now axial pointing down. And then just to draw the hydrogen, this hydrogen is equatorial pointing up. In which structure? And let me put numbers next to these. So are you referring to structure A or B? For the original ring? So to show you what this looks like, let me make a model for you. Let me make a model of this for you. Putting together the model right now. Give me one moment. Okay, here we go. Okay, So first and foremost, let's look at the ethyl group. So we clearly see that the ethyl group is axial pointing up. Now let's focus all the way in the back on this blue carbon for our methyl group. The hydrogen is pointing up, and is our methyl group, our Me, is it axial or equatorial? So looking at this methyl group right here, is it axial or equatorial compared to the hydrogen? So looking at this methyl group right here. Yep, it's equatorial. Yep, exactly right. And is it pointing up or down relative to the hydrogen? Is it pointing up or down? Looking at this methyl group. Is it pointing up towards my hand or down? Down, exactly right. So this methyl group would get a dash. Now, if we want to do a ring, does that make sense so far? Does that make sense so far? Okay, so after a ring flip, we're going to bring carbon number 4 up and carbon number 1 down. And I'd like you, now looking at the ethyl group, is the ethyl group equatorial or axial? Looking at this ethyl group now. Equatorial, yep, exactly right. And now looking at our methyl group, on our blue carbon, is our methyl group equatorial or axial? This methyl group right here. So look at, yep, exactly right, it's axial. And is it pointing up or down relative to the hydrogen? Down, exactly right. Perfect. Does that make a lot more sense now? Did I address the question? Okay, perfect. So we still have plenty of time to continue on with this class session. So what I want you to do now is let's focus just right now. On these first 2 questions. So I want you to focus on drawing chair conformations for the following structure. And if you go to view options, I'd like you to try and find the annotate key, and you can draw using the annotate key your proposed chair conformation for each of these structures. And I'd like, ideally within the next 3 to 4 minutes, to see about 1 to 2 structures for each of these dash wedge notations. So I want to see some student input on this page, ideally. But no pressure in that. And if you have any questions, don't be shy to ask. And if you want to share by bringing up a picture in your webcam, you're more than welcome to do that as well. I know it's hard to convey structures through chat, but the annotate feature is pretty good. Annotate should be available in the browser under the Zoom options, under the view options, I believe. If you're in the Zoom meeting, you have access to meeting controls and other annotation options. Worst case, we can work on getting everyone familiar with those options with a video tutorial that I'll have prepared during the weekend. Try checking around in the Zoom user options, and it should be available. So I already see a few students annotating. And in your actual chair conformation, you don't have to put the physical wedge. You just indicate that it's wedged by showing the relative position. But otherwise, it looks quite good so far. And would anyone like to propose a response for question for the second structure? And everyone's more than welcome to draw at this time. So I see a lot of reasonable, yep, the second substituent is an ethyl. Yep, exactly right. The attached to the dash is a 2-carbon chain that we call an ethyl. And I would recall line notation notes. Yep. And don't be shy, everyone else, to chime in. Just because 2 people are writing, you're more than welcome to write as well. I'll take a look at each of these before we clear them to discuss our final solution and the final conformations for each of these 2 structures. And we'll discuss in about 1 more minute. I'm seeing a lot of good work so far, so I don't just want to stop people while they have structures drawn. And don't be shy to type questions in chat about accessing the drawing tools embedded in Zoom. So the response in dark blue is perfect. Same with the response in pink for the first question. For the second question, the response in pink is almost perfect. The only thing that we'd have to make is just a modification, and I'll be redrawing these structures, but just to provide some real-time feedback, is you want to make sure you clearly indicate that your methyl group is axial. Other than that, it looks quite good. So what we're going to do is I'm going to clear the annotations and I'm going to draw out the instructor solution, but I really appreciate everyone participating, and I know it's a new experience drawing in Zoom, but it is compatible with a mouse and keyboard as well as a tablet. So I'm going to clear the annotations, I'm going to clear the drawings, and let's now go through the solution for this question. So first and foremost, we have a wedge. So this is axial up. So we're going to start counting axial, equatorial, axial, equatorial. Now we're going to count in a different color for our dashed, equatorial, axial, equatorial, axial. Okay, so we're going to draw our right-facing chair conformation. And we're going to put the methyl group, Me, in the axial up position. Now, we're also going to draw our hydrogen in the equatorial down. Now, based on the dash associated with this ethyl group, will this ethyl group be axial or equatorial according to our counting method? Will it be axial or equatorial? Axial, yep. This ethyl group will be axial, pointing down. And our hydrogen will be equatorial, pointing up. Exactly right, exactly right. Now, after a ring flip, we're going to bring carbon number 1 down and carbon number 4 up. And that in turn gives us the following chair conformation. So carbon number 1, our methyl group is now equatorial up. And at carbon number 2, our hydrogen is now axial up, while our methyl group is equatorial pointing down. Remember to still follow the guidelines for drawing axial and equatorial substituents that we discussed last class session. One moment. Yes, yep, perfect. It's parallel with this line here. Yep, we're good. Okay, does that make sense for question 1? Overall, the student responses were spot on for question 1. Let's now discuss question number 2. So again, we have a wedge. So we're going to designate that as axial up, and we're going to designate this as carbon number 1. We're now going to count around the ring. Axial, equatorial, axial, equatorial, axial, equatorial. And now we're going to count using our opposite color for the dashed. Equatorial, axial, equatorial, axial, equatorial, axial. So let's now process our first chair conformation. So we're going to draw our right-facing cyclohexane ring, and we're going to put the methyl group in the axial up position. Our T-butyl group, remember this group is called a T-butyl group. You'll get to know this specific alkyl group a lot because it's a functional lock for cyclohexane conformations. And my question to all of you, are we predicting this T-butyl group to be in the equatorial or axial position? Is T-butyl going to be in the equatorial or axial position? Yep, equatorial, yep. Has a wedge, so we follow our wedge counting method. So this is equatorial, but still pointing up. Okay, finally, at our adjacent carbon on the other side, would we expect our methyl group? Would we expect this methyl group to be axial or equatorial? This methyl group right here, axial or equatorial? Axial, exactly right. It has a dash, so we follow our dashed counting convention. Okay, so we're going to draw our methyl group in the axial down position. And our hydrogen, in contrast, is going to be in the equatorial up position. Now let's do a ring flip. In our ring flip, we're going to bring carbon number 1 down and carbon number 4 up. So our methyl group is still pointing up, but instead of being in the axial position, it's in the equatorial position pointing up. Our T-butyl group, instead of being equatorial up, is now in the axial position pointing up. Finally, looking at our methyl group in blue, so this methyl group, after a ring flip, will it be axial or equatorial? After a ring flip, will this methyl group be axial or equatorial? This methyl group in blue that I've starred. And don't be shy to type in chat. Yep, I see some equatorial responses. So this methyl group will be equatorial. So it's equatorial pointing down. And the way to really show that, again, I can't stress this enough, draw your hydrogens. So this hydrogen is axial pointing up. Is everyone okay with these two examples? Does that make sense to everyone, what's going on? You could, yes. There's a bit of an intuitive reflex on my part. In general, you never want to draw a structure with a T-butyl group in the axial position. And we'll see why actually when we discuss A values and steric hindrance. Almost always when you're drawing, like, it's not like it's wrong. Yes, it's due to the relative energy. When you have so the reason why you don't use dash wedge in these models is because dash wedge is used such that all of your normally drawn lines are perfectly flat in the plane of the page, while anything with a dash or wedge is above or below. When you're drawing chair conformations, what you're actually doing, where am I in this? Oh, okay, perfect. Sorry, I lost view of the camera for a moment. So when you're drawing a chair conformation, what you're actually doing is you're looking at your cyclohexane ring from almost a side-on view. So in that point, because you're dealing with a different perspective than that of dash wedge notation, it's inappropriate to use dash and wedge when you're drawing a chair conformation, because the chair conformation is a side-on view, while dash wedge, it's like you're looking at it as if the cyclohexane ring was completely flat and you're looking at what substituents are pointing out towards you or away from you. Does that make sense? Does that help clarify? So these two pictures are describing the same molecule, just different perspectives. And that's going to be really common in organic chemistry. So we still have some time left in our class session. So what I want us to do is let's tackle this next example, and let's try to do it within about 2 to 3 minutes. So break out the annotate feature and let's try to draw some responses for the two chair conformations for the following molecule. This time I'm starting you off with something with a dash. So you may have to adjust this molecule around. So dash or wedge. So essentially what you do when you decide dash or wedge is you look at your molecule from the side-on perspective. So exactly like your normal chair conformation. So you're looking at your molecule from the side-on perspective, and any substituents above the plane of the page or above the plane of your ring get a wedge. Anything below the plane of the page gets a dash. So it's not as if you're deciding whether you're looking at it from above or below. No matter which way that you choose to look at your molecule, you will draw different arrangements of dash and wedge, but you will be referring to the same molecule if you do that. For example, if you look at a molecule from this head-on perspective versus from this head-on perspective, I've just rotated the molecule. It's the same thing, but your dash wedge depiction will change. And we'll talk a lot more about that in chapter 5 with stereochemistry. And I really want to make sure we just try to keep things as simple and consistent as possible, because there's a risk if you start flipping your molecule around for you to accidentally draw something known as an enantiomer, which, although it looks very close to a mirror image, is actually a non-superimposable mirror image. But that's a really good question. So actually, it doesn't matter what view you look at your molecule from. If you're following exactly, oh yes, of course. Once we have our student input, I'm going to redraw the entire solution. This is just my way of helping students visualize what other students are doing and for getting some interactivity in this lecture. So it's not just me drawing every single structure. And don't be shy, just because one person is drawing, don't be shy to chime in with your own response. So the responses I've seen look pretty good so far. Let's now come together to discuss. So the first response is almost perfect. The perspective, though, on the first carbon, there's one thing you want to make really clear with your first perspective. So I'm going to clear the drawings, and then I'm going to start by drawing our solution. So first and foremost, I have full liberty to draw my hydrogen. So I'm going to draw my hydrogen with a wedge, right? Okay, and then I'm going to label for wedge, axial, equatorial, axial. And now I'm going to label for my dashed substituents, equatorial, axial, equatorial. Remember what I said before, you always want to make sure that on carbon 1, your axial substituent is pointing up. And this is to avoid accidentally drawing an enantiomer. So I'll show what I mean in a second. So our hydrogen's pointing up and our methyl group is pointing down. So it's our methyl group. Let me use the same notation that we've been using before. Our methyl group is equatorial down. Now, would we expect the chlorine here to be axial or equatorial following our counting method? Would we expect the chlorine to be axial or equatorial? Yep, axial. You can make the chlorine on the first spot. That's more than okay. But the second chlorine would be axial pointing down. There are actually a ton of solutions for this. And one thing that your book really likes to do is it likes to draw the same molecule 8 different ways and ask you whether or not the molecules are different. So don't be fooled. You can rotate and you can change your designation for carbon 1 around and you're still looking at the same molecule. Yep, so we're right. The second chlorine is axial pointing down. What about our third chlorine right here that I boxed with black ink? Is that chlorine going to be axial or equatorial? Yep, I see a lot of people typing axial. And will it be up or down? Up, exactly right. And now this is one thing that you really want to make sure you're being very neat about. You want to make sure if something is axial up, it's axial and pointing up. If you notice that like the way that you're drawing it, you always want to respect the relative position of substituents on each carbon for your cyclohexane ring. So that's one thing I would suggest you review in between this class session and next class session. So the second chlorine right here has a wedge. So this is telling us that the chlorine's up. So at carbon number 3, the up position is axial. So this chlorine is axial up. Also using our counting method, axial, equatorial, axial, we see clearly that the second chlorine would be in the axial position. So essentially the axial position is the position pointing up at carbon number 3. Does that make sense? Okay, perfect. So I'm going to quickly just show you the ring flip. So we exchange all of our axial and equatorial positions. Remember, carbon number 1 goes down, carbon number 4 goes up. So now we have our methyl, instead of being equatorial down, it's now axial down. Okay. And now our second chlorine is now, instead of axial down, it's equatorial down. And let's draw our hydrogen in the axial position, just so that way everyone can see. And then finally, our chlorine, which is now axial up, now turns into equatorial up with our hydrogen axial down. Does that make sense to everyone? In the ring flip, we just exchange all of our axial and equatorial positions. Now, and this is one mistake, since the first 2 substituents has a dash, they're treated like 2. Yes, that's one way of thinking about it. Yes, that's perfectly fine to think about. But what I really want to make clear in our last few minutes, is your first substituent at carbon number 1, if it has a wedge, you need to put it axial. If you're drawing the right-handed or the right-facing chair conformation. So although this is a really subtle mistake, this can cause huge problems. So one mistake that I see, and one thing that I don't want you all to draw, is we draw the let's suppose we draw the methyl group axial for some reason. We draw our chlorine equatorial. Oh, sorry. Yep, we draw our chlorine equatorial, and we draw our third chlorine equatorial. Now, this may not look like a big mistake, but on an exam, this would be a completely incorrect answer. Would someone like to explain why this structure I have here, that I'm just going to put a question mark next to, would someone like to explain what's so off about this structure that I drew? I preserved my relative stereochemistry, but let's just really quickly focus on what's up with that methyl group. Is it pointing up or down? And this is something that I want us to clear before we close off today's session. It's pointing up, exactly right. And the chlorine is now suddenly pointing up as well. So this structure right here, and one thing that I do want you to pay attention to, this one is not a ring flip. This is not a ring flip. Because do you notice how both of our cyclohexane rings, our chair conformations, are both both right facing in a way? So we haven't flipped the ring in this case. This structure is what is known, and I'd like you to remember this word as we'll bring back to it later on. This is known as an enantiomer, and it's where all stereocenters are flipped. So this is not a normal ring flip. This is not a ring flip. This is an entirely different compound. These 2 compounds are entirely different. And this is one mistake that I want to highlight. When you do a ring flip, you need to change yes, exactly right. So both the methyl and first chlorine are now wedge, and our third chlorine is now dashed. So this structure that we've drawn looks like this. So we flipped all of our stereo centers. And the reason why I tell you to always put the first substituent with a wedge in the axial position is to get around this common mistake. Does everyone see the difference between these two structures and how this second structure down here is not the same? It's a different structure. Okay, perfect. So the rules that I've showed you throughout this section are really important for maintaining consistency. Now what we're gonna do is we're gonna take a quick 10-minute break and then we'll resume for lab. I'm gonna lecture for about an hour and a half in lab and I'll be available to answer any lab questions. Just so that we can tie up the relevant material from this topic. Is everyone okay with that? And I'll be posting this recording to the Zoom cloud and then saving it to YouTube as soon as it's processed. Is everyone comfortable with that? Okay, so we'll resume at 7:10 for lab and we'll join the lab Zoom meeting. So I will see you all in laboratory in about 10 minutes. Yes, the lecture for lab will also be posted. Yep, I'm recording everything to the cloud, and once it's processed in the cloud, I can upload it to YouTube. So I am working diligently to process everything. It just takes a little bit for Zoom to get the recording processed and ready to go. But yes, I am working on that. Okay, perfect. So I'll see everyone in lab. So I'm going to end this meeting and we'll join the lab Confor Zoom meeting.